Okay, class, we're going to continue our discussion of thermochemistry, and we begin with a big idea. Heat flows from hot to cold. Heat flows from hotter objects to colder objects. I bet you've known that for a while, but let's imagine, this is actually a pretty important concept. Let's imagine the blacksmith who's heated up a horseshoe in a forge until it's red hot. He then drops the horseshoe in a container of room temperature water. What's going to happen? Well, thermal energy, Q, or heat, will flow from the horseshoe to the water until both reach the same final temperature. That is, we have an equilibration. But notice that heat is flowing from the hot object, the horseshoe, to the water, to the cooler object. But the flow of thermal energy in the reverse direction does not happen spontaneously, and that's the key. We cannot place a horseshoe into a container of water in which they're both at the same temperature and then wait for an hour or so and pull the horseshoe out and have it be hotter than the water. That is, to have the water's temperature go down and the horseshoe's temperature go up. Heat does not flow in that direction. Heat flows from the hotter object to the colder object. And that phenomena is actually very important for the second law of thermodynamics, which we'll get to at some point, no doubt. But let's further imagine this village blacksmith, since we like the village blacksmith, and he's heating a 1-pound iron horseshoe in a forge to a temperature of 425 degrees centigrade. Okay, and after he has heated this horseshoe up, he plunges it into a gallon of water. A gallon of water is 3.78 liters, with the water initially being at like room temperature, 25 degrees centigrade. Excuse me, I was interrupted looking at some photos of my grandkids. Okay, so after the village blacksmith plunges this hot horseshoe into the gallon of water, as we said before, there will be a thermal equilibration. Thermal energy will flow from the hot object to the cold object. And the question is, what will the final temperature be when both have reached the same final equilibrated temperature? We actually have all the tools, all the information already to solve this problem. Note that the specific heat capacity of water is 4.184 joules per gram per degree Kelvin, and the specific heat of iron is 0.45 joules per gram per degree Kelvin. So how do we attack this problem? Well, when thermal energy flows between two objects, we have from the first law of thermodynamics that the sum of the energy is zero. Energy is neither created or destroyed, but energy can be interconverted, or thermal energy can flow from one object to another. Or in other words, zero, the energy, the total energy of the system is equal to Q1 plus Q2. Or we can rearrange this and say Q1 is equal to minus Q2, where each of these Q, or thermal energy values, can then be described by the specific heat equation, which we had in the previous slide. That is, if we say that iron is our first component, Q1, the Q1 is equal to the specific heat of iron times the mass of iron times this delta temperature. And deltas are always final minus initial. So it's the final temperature minus the initial temperature. And that's going to be equal to minus Q2, 2 being our water, where we also know the specific heat of water. We know the mass of water, if we read above, and this is times delta T, which is the final temperature minus the initial temperature. So let's see, we know just about everything to solve to obtain the final temperature, right? Let's look at the next slide. This is the equation again, the specific heat of iron times the mass of iron times T final minus T initial is equal to minus the specific heat of water times the mass of water times, in parentheses, the final temperature minus the initial temperature. And again, as we said, we have just about all we need. We have the specific heat of iron. We have the mass of iron. We said it was a 1 pound or 454 gram horseshoe. All that times the final temperature, which is the unknown, times the initial temperature of iron, which was 425 degrees centigrade. And this is equal to minus And that minus is because we started with Q1 plus Q2 is equal to 0, and we rearranged it. So that's where that minus comes from. Minus 4.184 joules per gram per degree Kelvin, the specific heat of water, times the mass of water, which is 3,786 grams. Okay, we had that in a previous slide, that 1 gallon is equal to 3.786 liters, and the density of water is 1. So that's how we get 3,786 grams of water, times the delta T, which is the final temperature minus the initial temperature. The initial temperature for water was 25 degrees centigrade. So all we have to do is rearrange this and solve for the final temperature, which we can do. You can do the math, and the final temperature is 30.1 degrees Celsius or centigrade. Does this make sense? The bucket of water, the gallon of water was 25 degrees, and its temperature went up to 30.1 degrees, so it warmed up a little bit, as you would expect it to do if you plunged a hot horseshoe into it. And the horseshoe's temperature went from 425 down to 30.1. So it does make sense. Now note, in this type of problem, we don't really have to convert Celsius to Kelvin, and that's because the step size in Celsius and Kelvins are the same, and we're talking about a delta. If you want to go ahead and convert all your temperatures to Kelvin, you can do that. It'll just take you longer, but it won't make any difference in this particular type of problem because it's a delta temperature. Now on to chemical reactions and phase changes and some definitions of terms. If an energy change occurs as a result of a chemical reaction or phase change, this energy change can result in a production or transfer of thermal energy, Q, or work, W, between the system and the surrounding. For example, if there is a negative energy change for a chemical reaction or phase change that occurs within a system, this means, and this is our convention, that the energy level of the final state will be lower than the initial state. So the initial would be up here and the final would be lower. That's our definition of a negative energy change. And this negative energy change can result in a transfer of thermal energy or work from the system to the surrounding. That is, if we just focus first on the transfer of thermal energy, the system will appear to be hot as thermal energy is transferred from the system to the surrounding. I say that if your system is a test tube and you're holding it, and the reaction occurs in the test tube, and there's a negative delta E, it will feel hot to you because thermal energy will be transferred from the system, from inside the test tube, through your hand to the surroundings, and you are then part of the surroundings. We call this type of reaction in which thermal energy is transferred from within the systems to the surrounding, possibly through your hand, we call this an exothermic reaction. Okay? And similarly, if the energy change for a chemical reaction or a phase change is a positive value, this means that thermal energy will be transferred from the surroundings into the system, into the test tube, if the reaction is occurring in the test tube. In this case, if you were holding that test tube, it would appear as if it's cold because thermal energy is transferring from you, you're the surroundings again, from you into the test tube. We call this type of reaction in which there's a positive delta E and thermal energy is transferred from the surrounding into the system, we call this an endothermic reaction. So, the definitions. If the energy change has a negative value, is less than 0, this corresponds to an exothermic reaction. That's when it feels like it's getting hot. If the energy change is a positive value, greater than 0, this corresponds to an endothermic reaction. You got that? But in addition to a transfer of thermal energy between the system and the surrounding, an energy change can also produce work. Let's consider a simple case of a phase change type of process. Let's say the sublimation of solid carbon dioxide, dry ice, to carbon dioxide gas. When this happens, when solid carbon dioxide undergoes this phase change to gaseous carbon dioxide, there will obviously be an expansion because gases occupy a much greater volume than do solids. So let's imagine that this is occurring inside some system, such as shown in the bottom right, where the dry ice is in the very bottom part. And there's a sort of like a piston. So when the dry ice sublimes to the gas phase, it expands, pushes up the piston. Okay, what if we have a weight on top of this piston? Then the sublimation of carbon dioxide to carbon dioxide gas, as it expands, can do work. It can lift up this weight. So a chemical reaction or a phase change can also do work. In addition to thermal energy being transferred between a system and a surrounding, work can also be transferred between the system and the surrounding. Now, our definitions will be the same in this sense. When thermal energy is transferred into a system, it has a positive value. When work is done into the system, it has a positive value. Likewise, when thermal energy is transferred out of the system to the surrounding, it has a negative value. And when work is done by whatever is happening in the system on the surrounding, as in our example here where the sublimation of carbon dioxide, solid dry ice, pushes up the weight, that would be work done on the surroundings because the weight is in the surroundings. That process has a negative value for W, for work. So whenever Q or W goes into the system, it has a positive value. When either Q or W goes to the surroundings, it has a negative value. So in this particular case, let's think, if we're holding some test tube and it contains dry ice and it has this piston, first of all, when the sublimation of dry ice to carbon dioxide occurs, it's going to feel cold because that's the nature of that phase transition. So it's going to be an endothermic process, and thermal energy is going to be transferred from the surroundings, including my arm and including my hand, into the system. So I'm going to say the Q has a positive value. But in this particular case, work will be done by the expansion of solid dry ice to the gas phase. Work will be done on the surroundings. So while Q might be positive, W would be negative. Now, before leaving this slide, let me say also that this is an example of what is called pressure volume work. That is, the work is equal to minus P times delta V, just in case that comes up again. So what we said in the previous slide is the following, that when there's an energy change for some process, and in chemistry we're talking about chemical reactions and phase changes, that when there is an energy change, this can be equal to the sum of Q plus W, where Q is a transfer of energy between the system and the surroundings, and W is the production of work, or the performance of work, between the system and the surroundings. So in general, delta E is equal to Q plus W. We'll pause now and then come back and talk more about thermal chemistry.